Buttons are cool, but cranks are cooler. So let's add one. And I made at least 3 mistakes while planning this project, so keep an eye out. This is my crank. It's made from a rotary encoder and a popsicle stick. I'm going to put it on my flashcard thing instead of the red button I added last time. The first thing to do is get rid of that button. Now to plug in the crank. I'm going to need to modify it a bit. It has these little tabs that can be used to give a strong attachment to a circuit board. I'll just bend those out of the way. Now to start wiring it up. To know how to do it, we need to know a bit about how rotary encoders work. They have 2 signal pins, pin A and pin B. As you turn the encoder, pin A and pin B change between a high and a low signal. They're not in sync though, and they're not opposite of each other. They're a little offset, and it changes depending on which way you're turning. You can use these different signals to know which direction the encoder is being turned. To get this signal, you would connect pin A and pin B to a high signal, like 5 volts, with a pull-up resistor, and you'd connect the middle pin to ground. Unfortunately, I did not look at any example circuits before building this, so I did it backwards. It still works though. That's the first mistake. Now that we have a signal from our crank, we need something to do with it. I could hook pin A and pin B from the encoder up to the data bus like I did with the button, but then the Game Boy would only know that the crank is turning if it happens to check while it's turning. Right now, the code I wrote for the button checks the button state 60 times a second, so maybe that would work. And actually, I didn't think about trying it when I planned this project. That's the second mistake. Maybe I'll try it later. For now, I don't want to bother the Game Boy with trying to keep track of the crank itself, so I'm going to use these. They're 4-bit counters. You give them a clock signal, that's just a signal that alternates between high and low, and they count in binary up to 1111. I have 2 of them, and they can be hooked up to count all the way to 11111111, or 255. So if I wire them correctly and hook them up to pin A from the rotary encoder, then they will keep track of how much the crank has been turned. These counters can only count up though. If they could count down, then I could keep track of which direction the encoder was turned. But I don't have those fancy counters. Only these. First thing I'm going to do is wire up the load and clear pins so that the counter never gets cleared and never tries to load a value from their inputs. Maybe at some point later I'll try to make use of the load or clear pins to let the Game Boy reset or write a value to the counters. But not today. Next, I'll wire up power and ground, and wire up the clock signal from pin A of the crank. Now, the counters have 2 control pins, ENP and ENT. They control if counting is enabled, and they both have to be high for the counters to count. I have no idea what they stand for. If you know, please let me know in the comments. I'm going to connect EMP to 5 volts on both counters. That's going to be the main enable control, and I always want the counters to be counting. The ENT pin is going to be used to control the second counter. We only want the second counter to count up when the first counter goes from 1111 to 0000. These counter chips have a pin called RCO, or ripple carry out, that goes high when the counter is at 1111. So we connect the first counter's RCO to the second counter's ENT. That way, both counters will count on the first clock pulse after the first counter has reached 1111. The first counter will wrap around to 0000, and the second counter will go up by 1. Okay, the counters are all wired up to count. But what do we do with the outputs? We can't just connect the outputs directly to the data bus going into the Game Boy because that bus is shared with other memory chips. If we connect it like that, then the counters would muck up the signals for everything else communicating on the data bus. When I connected the button, I used some logic to only send power through the button when the Game Boy was trying to read from it. We can't just cut power to the counters though, since they'd forget their value. So this is where I made my third mistake while planning this project. I thought these counter chips had what's called an output enable, or OE pin. An output enable would be perfect for this. It lets you turn on and off the outputs of a chip. When the outputs are enabled, they can be high or low values. When the outputs are disabled, it's like they aren't connected to anything. It's called a high impedance state. Having these 3 states, high, low, and high impedance, is called tri-state logic. But these chips don't have an OE pin. So I'll add a chip that does. This is an octal D-latch. It is a little memory chip that can store a staggering 8 bits. I don't care about the storage part though. I care about the chip's OE pin. If I hook up the D-latch's load enable pin to 5 volts, it will basically ignore the storage part and send the inputs over to the outputs. Then I can use the OE pin to only enable the outputs when I want. So I'll hook up the counter's outputs to the D-latch's inputs and the D-latch's outputs to the cartridge's data bus. Okay, now how do we control the D-latch's OE pin? The OE pin is active low, so we need a low signal to turn on the outputs. I connected up this NOR chip for the button, but it goes high when the Game Boy is trying to read from the button. We need the opposite. We need an OR, and I have one. The connections are a bit different, so I'll need to rewire it. Okay, it's ready. Hopefully it works. Before I write any code for it, I'd like to test it a bit, to give me some confidence it's actually working. I can actually use the code from the button. The button code shows the word button when the button is pressed. So when you crank, it will look like the button is pressed over and over. Look at that. It's flashing button when I turn the crank. So maybe everything's working. Alright, for the code. What I want is to use the crank to control how much of an image is displayed. As you turn the crank, more of the image is revealed. I'm going to do this by starting off displaying a blank image. Then, partway down the screen, I'll switch to the revealed image. How far down depends on the value read from the crank. Now there's a problem. The crank goes all the way to 255, but the Game Boy screen only has 144 lines. The easy thing to do is just divide the crank value by 2, so it only goes to 127. That means the revealing will only start at line 128. So I'll make the bottom of the revealed image all black to make up the last 16 lines. And this is the code I've written to hopefully do all that. Just like the button code, it starts by waiting for VBlank. Then it turns off the screen. We need to wait for VBlank because if you turn off the screen outside of VBlank, it can damage the Game Boy. Once the screen's off, it sets the background palette and starts setting up VRAM. First, it fills tilemap 0 with all zeros. Tile 0 is going to be blank, so this makes tilemap 0 the blank image. Then it copies the tiles and tilemap of the graphic over. The tilemap data is written to tilemap 1. The last thing before turning the screen back on is to set up interrupts. I'm using these to know when to check the crank value and update the graphics. I want to check the crank once every frame, so I'm enabling the VBlank interrupt. That happens every time the Game Boy is done updating the display, so once every frame, or 60 times a second. This part here is going to be used for an interrupt that fires during HBlank. That's going to let me check if the Game Boy's reached the point where I need to switch images. Okay, now into the main loop. First thing is halt, so the Game Boy waits for the VBlank interrupt I enabled above. Then we clear the interrupt flag and read in the crank value. We get the crank value by reading from save RAM, and I'm going to be storing it somewhere, but I don't want to store it exactly. I want to store the line number where I'm going to be switching images. The crank value divided by 2 says how many lines before line 127 to switch the image. So the line to switch the image is 127 minus crank divided by 2. Dividing by 2 is actually really easy. It's exactly the same as an operation called shift-right logical. Now we have crank divided by 2 in register A. Register A is special. It's called the accumulator. Every 2-operand arithmetic operation the Game Boy can do uses the A register on the left and assigns the result back to A. That means we can't do A equals 127 minus A. So instead, I'm going to do A equals negative A, then A equals A plus 127. Now I store the result in register C. C for crank. If this were a more complicated game, I'd have to store the value somewhere in work RAM. But the code's simple, so I can afford to use the C register just for the crank value. Okay, now that we have the crank value, we need to wait until the right line to switch the graphics. I disable the VBlank interrupt and enable the LCD interrupt. The LCD interrupt can be configured using the stat register to interrupt on different things relating to the display. I set it before to interrupt when it reaches HBlank, which happens after the Game Boy has finished updating every line of the display. When the GameBoys in H-blank, we're able to change VRAM and update display parameters, like switching what tile map is being used. So now, we need to update the display. First, I have a special case for when C is 0, which is when we want the full image to be displayed. Since H-blank happens after drawing a line, if we waited till H-blank, we'd actually miss the first line. Once we know C isn't 0, we set the tile map to show the blank screen. Then we enter a loop to wait for the right line to switch, using halt to wait for the H-blank interrupt. Now we check if the current line is equal to C. If it's not, then we keep looping. If it is, then it's time to switch to tile map 1. And that's it. We switch back to the V-blank interrupt and do the main loop again. Let's see if it works. Alright, I copied over the ROM to the chip. Let's put it in. Turn it on. And let's crank. Looks like it's working. Now, like I said, it doesn't matter which direction you turn. It'll just make the picture go up. And when it gets to the very top, counter value will wrap around and it'll start back over from the start. So yeah, it's really neat. I'm happy that worked out. Alright, cool. That was a pretty fun project to work on. It brought together a lot of different things. Counters, D-latches, mid-frame effects to do the tile map switching. Yeah, I hope you all enjoyed it. And if you did, please be sure to like and subscribe. And if you want to help make more videos like this, I have a link to my Ko-fi in the description. Bye!